In this 39th lecture of this course, I'll discuss with rectifiers with you. The topic that we'll discuss today is rectifier, and one of the very first building block of a regulated power supply. I told you that in a regulated power supply, a regulated power supply means a commanded one or a controlled regulated power supply. I told you there are four blocks mainly. First is transformer, then you have a rectifier, followed by a rectifier, then this followed by a filter, and then you have a regulator, and then final output is given to a load. That this block diagram of a regulated power supply I have already discussed in the last lecture with you. So now our focus after this transformer is on this rectifier. Now what is this rectifier? If I say, what do you mean by this rectifier? First of all, is a rectifier here. Says this block, this represents a rectifier. What this rectifier does, or what is the function of this rectifier, that if you have an AC signal here, this type of signal is called a AC signal. That is where you have an instantaneous value. This is omega t, and it can be either a voltage or a current, or I can say suppose this is t. That is, it has some value on both on the positive as well as on the negative swings. So what this rectifier does, or the function of this rectifier, is to convert another type of signal which have a swing only either on the positive side or on the negative side only. Our focus will discuss it only on the positive side, that is, which converts this into this kind of signal, either this full wave, or it converts into even I say this type of signal. And this type of signal, this is called a AC. If I say that, if I name this is called an AC signal or a AC function. And this is called not a DC, but it is called a pulsating DC. It is called a pulsating DC. So now if I define that, what is this rectifier? So this rectifier is nothing. We said that this rectifier is an electrical circuit. It is an electrical circuit which converts AC into a pulsating DC. So an electrical circuit which converts an AC into a pulsating DC is called a rectifier. Now, as far as the classification of rectifiers is concerned, there are two types of rectifiers. Classification of rectifier. The rectifiers are classified into two categories. One is called half wave rectifier. Half wave rectifier. In short, I'll call it during my discussion as HWR. Half wave rectifier, and the other is called a full wave rectifier. Full wave rectifier. Further, this full wave rectifier is again divided into two parts. One is called center tap. This full wave rectifier, I'll represent this by FWR, in abbreviated as full wave rectifier. Again, the classification of this full wave rectifier is classified into two parts. One is called center tap. It is called center tap, of course, full wave rectifier. And the last one that we'll discuss is called a bridge rectifier. Bridge rectifier. So overall, this is the classification of rectifier: half wave rectifier and full wave rectifier. Further, this full wave rectifier is divided into two parts: center tap full wave rectifier or a bridge rectifier. And as far as the definition of this rectifier is concerned, rectifier is an electrical circuit that converts an AC into a pulsating DC. That is, this is not a pure DC. As I told you, the nature of this pure DC is like this. The kind of DC with respect to time, whatever, whether it can be voltage or a function, if you have function like this is called a pure DC. Let us suppose this is 5 volt here. It is producing constant 5 volt, but here this is not producing constant 5 volt here. It is a pulsating. It has some pulses here. So anyways, it is an electrical circuit which converts an AC into a pulsating DC is called a rectifier, and it is classified into two categories: half wave and full wave. Further, this full wave into center tap and bridge rectifier. So I'll start my discussion with this topic, that is a half wave rectifier first. So now I'll discuss this half wave rectifier. Now look at the, first of all, I'll discuss the circuit of this half wave rectifier. Look at the circuit diagram of this half wave rectifier. It has initially a transformer here, and for simplicity I am using a step down transformer. Means the number of turns in the primary are more than the number of turns in the secondary. And suppose I am using a diode here. This is a diode. This is a diode here. And followed by, there is a load resistance here. Then you have this load resistance. Means at the output I'll get a pulsating DC, and this is the simple circuit of a transformer. Now, suppose I say that here the input supplied here is a AC signal is supplied here. Supply voltage is this, and suppose I name this as Vs. This is supply voltage Vs. Now this voltage is being stepped down. I am assuming as a step down transformer. It can be a step up transformer also, but I am assuming this as a step down transformer here. And suppose I say that at the secondary of this is called the primary coil and this is called the secondary coil. And suppose I say that the voltage here, voltage at the secondary is, suppose I say that this is my input voltage to this rectifier. This will rectify, this diode will rectify this input AC. Now try to understand this. What is here? What I am saying, that you have this transformer here. This is a transformer, and I am taking only on this section of this transformer. This is a transformer here, and suppose I say that as I said that this is the input supply voltage Vs, and this has been step up or step down if the turns ratio of this, suppose I am saying that this is having n1 number of turns, and this is having, this primary is having n1 number of turns, and this secondary is having n2 number of turns, and the input here is Vi. This is V1 and V2. So V1 upon V2 is equal to N1 upon N2. That is, I can say Vs upon Vi is equal to N1 upon N2. Or I can say that this input voltage, this implies that this Vi is equal to, this Vi is equal to, of course, N2 upon N1 into Vs. N2 upon N1 into Vs. Whatever is the supply voltage here, it has been stepped down or step up. I am using a step down here. It has been stepped down by a factor of this much. That depends upon N1 upon N2. Now, the point is that here at this point, I have, suppose it is the supply voltage that comes in our households, that is, it is 230 volt and 50 hertz. This supply. At the input side, I am getting a step down voltage here. Say it is a 12 volt transformer, for example. So it has been stepped down here. The point is that. I hope that this is clear to you. And now this is my input voltage Vi, and suppose of course it is a sinusoidal voltage. I am drawing this input voltage here. Just see, suppose this is my input voltage. I'll draw it here, or I'll draw it here. Okay. Suppose the input voltage is this. I'm showing this here. This is VI. This is the input voltage, and the instantaneous value of this at any instant, the value of this voltage is, suppose I say it is Vm sine omega t. This is Vm sine omega t, where Vm is this. This is the maximum. With respect to omega t, I am showing here. And suppose I say that this is the voltage Vi. This is the input voltage Vi, that is the voltage between these 2 points, it is Vi. And suppose I say that this is 0, omega t, this is pi, this is 2 pi, say 3 pi, 4 pi, and so on. Now look at this circuit again. Suppose I say that this is the load resistance, and I represent this by RL. And this is a diode D. I'm naming this diode as D, and this diode is having some, say, forward resistance. I say that the forward resistance of this diode is RF. That is, the resistance offered by this diode is RF. Now during my discussion, we'll assume that it is offering a forward resistance RF, and I assume the bearer potential to be 0. We assume that the bearer potential for the time being is 0. And suppose I say that this is point A and this is point B. Suppose this is point A and this is point B. So let's see the working of this. What will happen, or let's discuss how this works, or how this converts this AC into a pulsating DC. I'll draw this here again. I'm dropping these points here. Now this is same, points have been dropped down, and suppose I say that this is omega t again here also. This is omega t. Let's find. Now what will happen? I'm saying that, remember that when diode is forward biased, it acts as a closed switch, and when this diode is forward reverse bias, it acts as a open switch. Now what will happen, that suppose I say that during the positive half of this input Vi, what I'm writing here, just see what I'm writing here. During the positive half, let's say working of this, during the positive half, I'm saying that during positive half of Vi, during positive half of this, positive means during this half, that is when this omega t is between 0 and 2 pi. This implies that when this omega, not between 0 to pi, between 0 and pi, omega t is between 0 and pi. When omega t is between 0 and pi. Now under this condition, if you see that, suppose I say this is, of course this point is grounded here, this is grounded here, this is at 0 potential, this point, this B is at 0 potential, and if you see that this A, suppose it is 1 volt, 2 volt, 3 volt, 4 volt, 5 volt, 6, 5, suppose this is 10, 9, 8, 7. So if you look at this point, let me show on a separate page here. Look at this here, this D, this is your diode D here, this diode D, this is point A, and of course this point is connected to B, this is B here. A is at higher potential as compared to B during the positive half cycle. This A is at higher potential as compared to B. It means that this diode is forward biased. So I can say this implies that D is forward bias. I am writing FB. This FB stands for that this is forward bias. So I hope this is forward bias. So it acts as closed switch. It acts as closed switch. Let me use another. It means it acts as a close switch, and it is offering only a forward resistance. See what is happening, that during this time I can say that under this condition, when this is positive, A is positive, I am saying A is positive with respect to B, So what is happening, that this diode is offering a resistance RF here. RF, of course this is RL here, load resistance RL, and this is simply, I can say, I'll show a switch here. This is a switch here. It is acting as a closed switch here. And this is the condition when for forward bias. This is the condition when omega t is between 0 and pi. So naturally what will happen, that the current will flow in this circuit in this direction. This current through this load. Suppose I say that the current flowing here in this load, suppose I say that the current flowing here is IL. So current will follow this. So you will have an output like this. You'll have a current like this. Now what will happen during the negative half, if you see? I'm saying during the negative half. During the negative half cycle rather. Let's do one more term here. I missed here. During the negative half of Vi. Negative half means this half I am talking about. During the negative half, that is omega d between pi and 2 pi. When omega t is between pi and 2 pi, what will happen? When B is this B is negative. This is, if you see, A becomes negative now and this is positive. So it means say that diode D is a reverse bias. See, this is negative. I am talking with respect to point A. I can say that in this case A is positive with respect to B. Now B is positive with respect to A. Means A is negative with respect to B. It means this diode is reverse bias and it acts as open switch. It acts as open switch. See, I am showing this here. Second case. You have this point A and this is point B here. Now what is happening, that this diode D, it is acting as a open switch here. This will act as a open switch, and if this is the load resistance RL here. So what will happen? This means that no current flows here. It means that the value of IL is equal to 0. This is the case when omega t is between pi and 2 pi under this condition. No current is flowing through the load. So I am showing this as 0 here. Again, when this further again this during this positive half cycle, the same thing will repeat, that A is more positive with respect to B, diode D is forward biased, and of course this output current will follow this input voltage here. Again this will be 0. Further again, when this is forward biased, this diode will be forward biased. So during the positive half cycle, during this positive half cycle, this diode D is forward biased, it is acting as a closed switch, and during the negative half cycle, current is flowing in according to the input signal here. Say, I'll say this is IL. IL means current across this load. IL. Same is here. This is 0, this is pi, 2 pi, 3 pi. Same points has been dropped down here. So under this condition, this diode is reverse biased, so it is 0. Under the during the negative half cycle, this is reverse biased, of course 4 pi, and so on. And this is the current which I obtain. And here I can say that the instantaneous value of this current, if you see, the instantaneous current value of this current, I can say it is, I can represent this by Im sine omega t. See, under this condition, what is the current flowing in this circuit? Between 0 to pi, I can say that this IL, load resistance, which load current, or current through this load I or IL is equal to Im sine omega t, and under this condition between pi to 2 pi this load current IL is equal to 0. Now what is the value of this Im? This is Im. If you see this, I am saying that this is Im, maximum value of this output current, means current through this load. Current through this load is Im sine omega t. And what is Im? Im will occur when this V is equal to Vm. Im will occur when this V is equal to Vm. Now suppose I say this is the condition when V is equal to Vm. I am drawing this again here. This is the condition. See, suppose I say I am taking only that case when V is equal to Vm, when this is maximum. Let's take this one. This, of course, A is positive. You have this RF. Look at this. This is RF and this is RL. RF and this is RL. When this V is equal to Vm, under that condition, I can say that this I is equal to Im. So if I find that what is the value of Im? Im will be Vm, V upon R, and these two resistance are in series. So I can say it is equal to Vm upon Rf plus RL. Where, so I can say that this I is equal to Im sine omega t, and this Im, where this Im is equal to Vm upon Rf plus RL. I hope that this is clear to you. This is the working, and remember that whatever mathematical expression we'll discuss, input is this. Input is, when I say input to the rectifier, means the input, or it is the input or the voltage which is at the secondary of this transformer. This Vi is nothing, it is the secondary voltage of this transformer. So I'll stop it here. I'll continue in the next lecture. Thanks for the time being.